The Burj Khalifa uses ice in its concrete. Not for decoration, not as some symbolic gesture, but because without it, the building physically couldn't exist. When you're pumping concrete over 600 meters vertically in desert heat exceeding 40 degrees Celsius, normal concrete simply doesn't work. It hardens before reaching the top. So engineers mixed ice into the concrete to drop the temperature enough for it to remain workable during the 3-hour journey upward. That's the kind of problem solving required when you're building something taller than anything humans have ever built before. As of 2026, the Burj Khalifa still holds the title of world's tallest building at 828 meters, nearly 500 feet taller than second place. But what most people don't realize is how much invisible engineering separates these structures from total collapse. The secrets aren't in the glass facades or observation decks. They're buried in foundations, hidden in elevator shafts, and suspended in giant pendulums most visitors never see. Right now, only 4 completed buildings on Earth exceed 600 meters. They're called megatals, and they represent the absolute limit of what we currently know how to build. 9 of the world's 10 tallest buildings are in Asia. Only One World Trade Center in New York represents the Western Hemisphere. This isn't coincidence. It reflects where the expertise, ambition, and frankly the money to solve seemingly impossible engineering problems currently exists. Let's start with the foundation of the Burj Khalifa, because that's literally where everything begins. The building sits on 192 reinforced concrete piles, driven more than 50 meters into the ground. The foundation alone required 45,000 cubic meters of concrete. That's roughly equivalent to 18 Olympic-sized swimming pools worth of material, just for the base. But here's what makes it fascinating. The engineers couldn't use regular high-strength concrete because of subsurface water at the construction site. They had to develop an entirely new mix that could withstand aggressive underground conditions while still being pumpable to extreme heights. The pump system they created broke global records. It had to move concrete vertically over 600 meters, and the specialized mix developed by BASF had to maintain workability for over 3 hours before hardening. Think about that challenge for a moment. You're essentially asking concrete to defy its own nature, to stay liquid far longer than it wants to while being pushed through pipes to heights where the air pressure itself becomes a factor. But the foundation is only half the battle. Wind becomes your primary enemy at these heights. The Burj Khalifa's distinctive Y shape isn't aesthetic preference. It's a weapon against wind. Each wing has its own high-performance concrete corridor walls and perimeter columns that buttress the others via a hexagonal central core. This design was engineered to confuse wind as it approaches the building. Wind tunnel testing proved the shape breaks up wind vortices that would otherwise place catastrophic structural stress on the tower. The tapered form and staggered setbacks disrupt wind patterns and reduce vibrations that would make the upper floors uninhabitable. During construction, up to 12,000 workers were on site daily in temperatures exceeding 40 degrees Celsius. Moving that many people 163 floors up and down presented its own engineering puzzle. The solution was double-deck elevators, each capable of holding 14 people per deck, running in pressurized environments. Pressurized because at those heights, even elevator operation requires accounting for atmospheric differences. Now, Shanghai Tower took a completely different approach to the wind problem. The building twists 120 degrees from bottom to top, and this isn't architectural flair. That twist reduces wind loads by approximately 24%, making it one of the most aerodynamically efficient skyscrapers ever built. It's 632 meters tall, making it the world's 3rd tallest, and it demonstrates how form and function can merge when engineers get creative. The tower consists of 9 cylindrical buildings stacked atop each other, totaling 128 floors, all enclosed by a double-skin facade. That facade has an inner layer and a transparent outer layer, creating an insulating airspace that regulates internal temperatures and dramatically reduces energy consumption. But what really makes Shanghai Tower remarkable is what you can see on floors 125 and 126, a 1,000-ton tuned mass damper. This is where skyscraper engineering gets truly wild. The top of Shanghai Tower can sway up to 1 meter during strong typhoons. 1 meter. Imagine being in an office on the 100th floor while the entire building moves a full meter to one side. You'd feel it, right? Except you don't. You barely notice. That's what the tuned mass damper does. It's essentially a massive pendulum that counteracts building sway caused by wind and earthquakes. When the building starts moving one direction, the damper swings the opposite way, cancelling out the motion. But the technology behind these systems has evolved far beyond simple pendulums. Much of this effectiveness comes from magnetoheliological fluid, a substance that sounds like science fiction but is very real. This liquid changes to a near solid when exposed to magnetic force, then back to liquid once the force is removed. During an earthquake or severe wind event, the fluid inside dampers shifts between solid and liquid states as tremors activate magnetic forces. It's reactive engineering at its finest, materials that respond in real time to threats the building faces. Taipei 101 in Taiwan uses a 730-ton ball that moves to stabilize against winds reaching 130 miles per hour. The Comcast Center in Philadelphia takes a different approach entirely. 300,000 gallons of water in a tank acting as a counterweight. Same problem, completely different solutions. What matters is that all skyscrapers move. The tallest ones can sway almost a meter on each side during seismic events or strong winds. These damping systems don't prevent movement. They make it survivable, imperceptible to the people inside. Which brings us to what's happening right now in Saudi Arabia. Jeddah Tower is about to shatter every assumption we have about building tall. As of June 2026, construction has surpassed the 103rd floor and cleared 400 meters in height. When completed, possibly by 2028, it will stand over 1,000 meters tall, 1 full kilometer, the first structure in human history to reach that height. The project had a turbulent history. Construction halted in January 2018, when the tower was about 1/3 complete, frozen for nearly 5 years due to labor issues following Saudi political events and the pandemic. But work resumed in 2023, and since January 2025, construction has been moving fast. Adrian Smith designed this one too, the same architects behind Burj Khalifa. He clearly learned something the first time around. Jeddah Tower's engineering philosophy is radically simple. No columns, no outriggers, no floor beams, spandrel beams, or vertical transfers. The structural system consists entirely of interconnected walls, with each element resisting both wind and gravity loads simultaneously. Thornton Tomasetti, the engineering firm, explained their approach by noting that concrete is king in the Middle East. They're using regional construction practices and concrete strengths common to Saudi Arabia, making the tower faster and cheaper to build than you'd expect for something this ambitious. The foundation system is anything but simple. A 5-meter thick raft foundation sits on 270 board piles, each 1.8 meters in diameter, extending to depths of 105 meters. That's deeper than the Burj Khalifa's foundation. It has to be. You're supporting a structure that will stand 180 meters taller than the current record holder. The tower's 3-petal footprint serves the same purpose as Burj Khalifa's Y-shape and Shanghai Tower's twist. Aerodynamics. At a 4-kilometer high, wind isn't just an engineering consideration. It's the primary design constraint. Those 3 petals shed wind vortices and reduce structural sway at altitudes where weather patterns become genuinely unpredictable. What's remarkable about the current generation of super-tall buildings is how they've evolved beyond simple height competitions. Modern skyscrapers integrate office space, luxury residences, hotels, retail, and observation decks into single vertical ecosystems. Shanghai Tower collects rainwater for internal use and has 270 vertical wind turbines near the top, providing 10% of its electricity. It uses 21% less energy than comparable American buildings and 54% less than Chinese efficiency standards require. These aren't just tall buildings anymore. They're complex financial assets, transport-linked ecosystems, engineering laboratories. The first generation of skyscrapers was about cramming floor space onto expensive urban land. The second generation was prestige, global branding, national confidence. This third generation is different. These towers compete for talent and capital, functioning as mixed-use environments that maintain activity 24 hours a day. They're tourist attractions generating revenue beyond traditional leasing models. When Shanghai Tower's concrete pour happened, it took 63 continuous hours, using 450 mixer trucks and 8 pumping stations around the city. The building sits in an earthquake zone, so its 980 foundation piles extend 85 meters deep, making it resilient to magnitude 9 earthquakes. The elevators travel at 20.5 meters per second. You can ride from ground level to the observation deck faster than most people drive on the highway. Each of these towers represents thousands of people solving problems that didn't exist until someone decided to build higher than anyone thought possible. They're pushing concrete beyond what it wants to do, designing shapes that trick wind into flowing around rather than against, and creating damping systems using fluids that change state on command. Every solution creates new problems at the next height threshold. Jeddah Tower will face challenges we haven't even identified yet. That's what makes this compelling. We're watching the limits get rewritten in real time, one floor at a time, until someone plants a spire at 1 kilometer and proves it can be done. And that's just the beginning. Because once Jeddah Tower tops out at 1 kilometer, someone else will start planning for 1,200 meters, then 1,500. The engineering challenges scale exponentially with every 100 meters, but so does human ambition. These buildings aren't really about height anymore. They're about proving what's possible when you refuse to accept that something can't be done. Every megatall tower stands as evidence that the impossible is just expensive and difficult, not actually impossible. The next time you see one of these structures dominating a skyline, remember what you're actually looking at. It's not just steel and concrete and glass. It's ice mixed into desert concrete at precisely calculated temperatures. It's magnetophysiological fluid shifting between liquid and solid thousands of times during a single storm. It's 270 foundation piles driven 105 meters into bedrock. It's 12,000 workers in 40-degree heat solving problems most people will never know existed. That's the real secret. These buildings exist because thousands of people decided the laws of physics were negotiable.